Right, so we're on the home stretch now, doing random graphs at last. As I mentioned before, random graphs were invented for existence proofs. So the famous theorem is the R.Diestel theorem, that there exist graphs that simultaneously have arbitrarily large girth and chromatic number, and the way he proved that was that he set up a probability space, and rather than constructing these hard to construct examples, he just proved that in this suitable probability space, the measure of those graphs that have these desired properties is bigger than 0. So indirectly, the existence of such graphs is proved in this way. And we also noticed that in the Ramsey context, lower bounds need constructions, right? You need to construct a two-coloring of the edges of a graph without a monochromatic subgraph of desired shape in either color class, or say a complete graph in the graph itself or in the complement. And rather than construct such things, one can likewise in the same fashion use random graphs to prove such lower bounds for Ramsey. We'll see both examples in this section. We'll do the Ramsey bit today, which is really, really easy, and R.Diestel's theorem next time. Now, random graphs, of course, are also studied in their own right now. So you can ask, with what probabilities do random graphs have this or that property, and how are these related to each other, and so on. We'll get to that in the third lecture just a little bit. And so today I'll be very, very pedestrian in setting up the formalities for random graph theory. When I was a student and I was first taught random graphs, what happened to me was, I think what happens to most students, that they're just told, well, it's easy. You just flip a coin for every potential edge, and then you get some outcome, and there's your random graph. So I thought, aren't we doing mathematics? So I couldn't sort of make this precise at all. And it's really easy to make precise, but it's also easy to forget that it takes a thorough look to square this with all the mathematics that you have learned, like what is a probability space, for example, and so on, what is a measure. And what I'll try to do in my approach to random graphs, which is perhaps slightly more elementary than others, is to get these basics really, really explicit, so that after that, when you hear random graph jargon, you can always go home and say, yeah, I can make this precise. But I'll try to put you in a position where you can make this precise by going through all these details quite explicitly. And I'll avoid probabilistic jargon whenever I can. Of course, we'll be using things like expectation and the expected value of a random variable and so on, but I'll tell you what these things really mean. I'm not assuming that you've done probability. You may want to look up the definition of a probability space. Even that I think I'll probably mention later, but that's all you need. Okay. Nonetheless, before I get formal, let me describe what is the aim here. So the set of all graphs on some fixed set of vertices, namely the integers from 1 to n minus 1. So there are n vertices, and there's one fixed set of vertices for the rest of eternity. Right? So we want to turn that into a probability space. So a single graph on this set of vertices will be an element of this space. Okay? Now, what's a probability space? Here we just have a finite set, namely the set of all these graphs that are possible on this set of vertices. That's a finite set, quite unlikely for probability spaces, but in our case, this is a finite set. And there's a probability measure on it. So the subsets have a measure and a number between 0 and 1. The empty set has 0. The full set, a set of all graphs on this set of vertices, has the measure 1. And this measure is additive in that disjoint subsets. You can add the measure. So the measure of the union of two disjoint sets is the sum of the two measures. And that's it. That's all. So normally you have something like sigma additivity and so on, which we don't need because we're finite. So that's it. Nothing mysterious about it, except you may want to look up what a measure is, but I'll mention the one tricky part where you might need that later. Okay, it's important that we always have the same set of vertices. And so you might ask, well, don't we want to study arbitrarily large graphs? Why fix the set of vertices? Then we can only study random graphs up to whatever n is, 17 vertices. Well, no. N will be allowed to vary, but it's important that we have a different space for every n. Now, if you have done probability, here's a nice little puzzle to think about. Why don't we define a probability space on the set of all finite graphs? Okay. You run into a problem if you wanted to do that. Of course, one can do it, but it's not going to be very helpful. That's an aside for those of you that like probability. And so let me continue here. We have this space. We have single elements that are individual graphs, or individual graphs on this set are single elements of that space. Now, graph properties. So, for example, like contains a cycle, right? They become subsets, namely those elements of this space that have this property. And in probabilistic jargon, subsets of the probability space are just called events. Don't worry about why. They're just called events. Okay? Now, in particular, properties in the sense of subsets that are closed under isomorphism. So if one particular graph is in your subset, then all isomorphic copies of that, and there might be more than one on n vertices, are also in the set. So they would be given by a graph invariant. So graph invariants are what? They're maps that assign to every element of our space something. For example, a number, like the chromatic number assigns to every graph on this particular set of vertices its chromatic number. All right? Maps defined on the probability space are, shall I say, unfortunately called random variables. There's nothing random about them, and nor are they variables. they're just functions. So I don't know how this came about. It's probably that people were interested in, I don't know, things they didn't quite know and had to sort of treat probabilistically, like, I don't know, properties of some people that they couldn't investigate, and these properties, if they were numerical properties, were unknown to them but interesting, and things that are unknown are called x, and something that is called x is a variable. So that's my, maybe it's not true, but I mean, yeah. Just when I say random variable, I mean a map on this set, and that's it. Okay. And random variables have expectations, so the expectation of such a function is just the integral. Yeah, that'll come later. Okay. Oops. I think I've said everything I want to say about the idea. So, we want that these graphs, or we want to mimic what I told you earlier. When I was a student, I was told, well, just flip a coin for every edge, for every potential edge, and the outcome is your random graph. Right? So we want these events, let me call them A. E, that's a little e. And the E is a potential edge. So that's a true set of vertices. What's this event? An event, by definition, is a subset, sorry, not of this, a subset of our probability space. So that's the set of all G. When I write G for graph, then it's always a graph on this. So I won't repeat that every time. That contains, or that contain, this particular potential edge. Right? The edge between 3 and 7, the potential edge, some graphs on the vertices from 1 to 17 contain this edge 3, 7, others don't. And the set of all those that do is a subset of all the graphs on this vertex set, and this subset is the event E, the event that E is an edge of the random graph. So we want these events to be independent for different E's and have probability P for some fixed P. This is a number between 0 and 1. Right? And so that will be written as the probability, and then I write the description of the event in there. So like that. So what is that? That is going to be the measure, the probability measure of this subset AE with respect to the measure that I haven't defined yet. But I want this measure to have these two properties, that these events all have the same property, probability little p, and they have to be independent. I want them to be independent. Okay, here's another one. What is independent? We're not two, it's something that we say about events. So when our two events, here's our probability space, and there are some events A and B. So subsets of our space, when are two subsets independent? Well, the definition you've all heard before is that two subsets are independent if the probability of them both occurring is the product of their probabilities. Yeah. Why is that called independent? I never understood it. So here's, it's totally trivial, but one has to think about it. So what is an intuitive way of formalizing the notion of independence? Well, A is independent of B if the measure of the portion of B that also has the property A, that also lies in A, i.e. the intersection, so probability of A intersect B, the proportion of that of all the things in B should be the same as the proportion of those things that have property A in the whole space. All right? So the chance of A happening, if you consider it globally in the entire space, should be unaffected when you restrict your attention to those things that happen to have property B. Then the portion of those that have A should, relative to that, be the same as it is globally. That is my contention of a sensible notion of independent, but of course, it's the same as saying that P of A intersect B, is the same as P of A times P of B, because that is 1. Right? So here is your definition as you usually learn it. And this is the way I remember it. Now, notice that I wrote A independent of B here to give you the intuitive idea. It's not at all clear from this intuitive idea that that's the same as B being independent of A. But this is symmetrical in A and B. So a corollary of this deep equivalence here is that A is independent of B in the sense, if and only if B is independent of A. Okay, so we can't get more elementary than that. Yeah, so formally, I won't write it down. A set of events is defined to be independent if for every subset of that set of events, the probability of them all occurring, of the intersection of this subset, is the same as the product of all the probabilities. Right? We don't need that just for two, but for sets of events. Okay. Now, if P is such a probability measure on omega, which, by the way, we'll later denote as G of NP, then we can easily compute the measure of a singleton set, of a singleton subset of the space, right? So if, I'll just write it generically. So what's the probability of one particular graph on this vertex set occurring? So the measure of the set that only has this one element. Well, we want these events E, A, E to be independent. So we'll have the product of, do I want to write? No, I don't want to write it that way. No, just, so little p is the measure of this, of little e, one fixed little e, no matter which, occurring. And if G has a certain number of edges, then we need all these edges to be there. So G lies in the intersection of all these things, and all the non-edges of G really shouldn't be there. So we'll have Q, and Q in probability is always shorthand for 1 minus P, right? And then we'll have n choose 2 minus the number of edges, all the non-edges, the number of non-edges. So all its edges have to be there, all its non-edges have to be absent. And once you've asked all that, you've made lots of independent assumptions. The probability of that happening, which is exactly the measure of the unique graph that satisfies all that, is this product. But since we're in a finite space, once this is clear, the entire probability measure is determined. And that is by additivity. I take an arbitrary subset. What's its measure? Well, it's the sum of the measures of the individual singleton subsets, right? Because they're disjoint. So these two assumptions define our probability measure uniquely. So all we need is that such a measure exists. Okay, now if you look at this line here, our next task is to construct such a measure. That might remind you of something you've learned in your analysis course, namely of the definition of a product measure. Right, so remember that when you have, say, R squared or something, the measure, as you defined it when you did integration and stuff, the measure of such a box was defined as the product of these two measures in R1. Just like here. And then, and this is the little bit about measures that I alluded to earlier that one needs to know, defining the measure on these boxes defines the measure via additivity on the entire space. All right, so you need sigma additivity for Rn, and here you just need additivity of disjoint sets, in fact, of singletons. All right, so the measure of this box is defined as, let me write, A cross B is defined as the measure of A times the measure of B. That's the definition of the probability measure. Right? Just on the set of these very specific subsets, but by additivity that defines this measure on all measurable sets, and here everything is measurable. So that's exactly what we get if we set it up in this way. So define which way around? omega p. So omega is our space, and p is the probability measure, as the product of the spaces omega e, pe, over all potential edges, e in V2. Now I have to tell you what these are, well, the obvious things. So with for every e, omega e has two elements, a 0 and a 1. And I'll write an index e here, just not so as not to forget that we're in this very particular space. So I'm creating a space, one little space for every potential edge. And the entire space is going to be the product space of these tiny little spaces. So PE of, let me write 1 first, of 1, PE of the event singleton 1 is P, and PE of singleton 0 is Q. And that's it. Right? Well, now the definitions are all in place. What you can now do is apply this definition and check that these two assertions are indeed true, that these events, A, E, do have this probability, right? They're all P. Of course they do. What's the event AE? What is an element of this space? An element of a product space is a function that assigns to every element of the index set one element of the union of all these spaces in such a way that the image of such an index lies in the factor that it indexes. So a function that assigns, in this particular case, to every potential edge E, either a 0 or a 1. And this choice for every little e of a 0 or a 1, all these choices together are this one function. So you can think of an element of this space as a graph. Namely, for every potential edge, you have chosen 0 or you have chosen 1. And what's the measure of the event AE? Well, it's the subset of all these things that, in the case of our particular chosen E, choose 1, and in the case of all the other E primes, choose either 0 or 1. So what's the value of that measure? Well, it's little p times the measures of, in the other coordinates, the entire space. So lots of 1s. So I've now given you an oral proof of this. And an oral proof of that will be pretty much the same. Right? You have your chosen subset of little e's, and the event of them all occurring is the set of all those functions that assign 1 to those e's that you have chosen, and 1s to the other coordinates. So that's precisely this product, by definition of the product space. So you can read it all up. I mean, the proof is totally elementary. Just make sure the definitions are really followed, and your intuition has no place here. Just follow the rules, right? And that will give you some security later when you have to deal with this. And you can sort of put up with people using jargon without feeling at sea. Okay, questions? No, good. Right, so let's look at some examples. Let's fix a graph H on a subset of V, right? And then we can ask, what's the probability of this occurring in our random graph? So the probability of this event, what is this event? This event is the set of all little g's that contain H. Not an isomorphic copy of H, this particular H, with vertices 3, 7, and 21. And 3 is adjacent to 21, and so is 7, but 3 and 7 are non-adjacent. Right? That's one particular H, and it's very, very important that this is not unlike the usual way we use this relation. This is for a very concrete fixed graph, not for an isomorphism type of H's. Okay, so what's that? Well, we'll have to make sure, say with k vertices and L edges. We'll have to make sure that all these L edges are in G. These are L very particular concrete edges. So we'll need P to the L for this to happen. How about the non-edges? We don't care, because we just want H to be a subgraph, not necessarily an induced subgraph. So when H has a non-edge, this corresponding pair of vertices may be an edge or a non-edge of G. We don't care when we consider subgraph. So that's it. If we do care, so we're considering induced subgraphs, then it's P to the L times, the required non-edges. What if we don't consider a fixed H, but just ask what's the probability of G containing any triangle, or say our particular subgraph path of length 2, as an induced subgraph or as a subgraph and so on. And that is much more complicated, right? So the things to play with is additivity, but in order to use additivity, you have to make your events disjoint, and independence whenever it applies. So those are the tools you can play with, and then you have to look at various possible ways in which whatever isomorphism type of H you want to occur in your G, and you get some complicated expression. Let's do it for a very simple case, namely for H being a complete graph, right? So the probability of a complete graph of order k occurring somewhere in G, not a particular complete graph, but just any complete graph of order k. So to make it less confusing, I'll write omega of G being at least k. Right, omega, have I introduced this before? Probably not in graph theory 1. So this is the clique number. Omega is the largest R such that KR is in G and now this is not a particular KR, but just any KR, right? And that's the clique number. And similarly, we have the independence number, that's called alpha, fittingly, if that is omega. So that's the largest R such that KR complement is found in G induced. Independence number of G, right? Okay, so G, the event that G has a KK is rephrased by just saying that the clique number is at least K. Okay, so what's that? Okay, when you fix your desired copy of your KK, you want all these edges to be there, so for this particular copy, you need all these edges to be there. Now, there are many ways of finding a K-clique in G. How many ways are there? Well, you need to choose K out of n vertices. So there are so many choices of the vertex set of your KK. And then for that vertex set to be really present, you need these probabilities. But now these events are not disjoint. And this probability is the measure of the union of all these events, but this is not a disjoint union. Right? So we don't have additivity, we only have this. Yeah. And in the same way, we have this is the same for the independence number. Like this. Okay. And here comes the Ramsey bound out of the blue. That's all. We haven't done anything, right? So here comes Ramsey. What number? That's 1113. The Ramsey number of k. So what's that? That is the smallest n such that a two-edged coloring of Kn has a monochromatic Kk. Or in the other setup, it's the smallest n such that for every graph on n vertices, either this graph contains a Kk or its complement contains a Kk. And the theorem is that this is less than 2 to the half k. Now, this is quite remarkable because the upper bound that we had was 2 to the 2k minus a little bit, minus 1 or 2. And that was an easy upper bound. So when your n is at least 2 to the 2k, then no matter how you two-color the edges, you will find a monochromatic kk. But this tells us that there exists a two-coloring of the edges of a complete graph of this many vertices without a monochromatic kk. Or, in other words, there exists a graph G on this number of vertices that doesn't contain a kk and whose complement doesn't contain a kk. So this G doesn't have a k. The omega of this G is less than k, and so is the alpha. Okay, that's what this says. This says for n as large as this figure here, there exists a graph G whose omega is less than k and whose alpha is less than k. And this is how it's proved. So show that for all n all the way up to 2 to the half k, the probability of omega being at least k, and the probability of alpha being at least k, are both less than a half. So there exists a G on n vertices, even if n is as large as that. There exists a G that is outside both events. That's it. Right, so, and how do we find this n? Well, it's totally easy. If you start with n small, like k, right, then this is 1. And this is, I don't know, something less than 1 to some big power. So this is small. So is this. But this big power, although it may be big for k big, is constant, whereas n is variable. Now we're playing with the n, having fixed k. K is arbitrary. This is true for all k, right? But we will fix k at the start, and then we'll play with n and show that up to this n, all this is true. And once we fix k, these are constants, and we can just let n grow from k all the way up, as long as these probabilities are still less than a half. So, yeah. And there's a little bit of calculation in there, and you can read it up in the book. But that's the idea. Very, very simple. Questions? Okay. Okay. Next thing, the expected value. Now this is jargon, but I'll make it precise. So the expected value of a random variable x that assigns to every graph in our space some non-negative number. That's important for everything that follows now. Right? So if we have such a function which assigns to every graph, to every element of our probability space, some non-negative number, then that's the expected value, is written as like this, and E, this operator or function or whatever, E is called the expectation. Right, so that is defined as, well, let me do a picture first. So X, this is G and P. I want a very particular picture. All right, so here are all the graphs. Since we're finite, I'm assuming that an interval here corresponds to a graph. No, so the elements are not these dots, but the elements are things between the dots. And let's assume that the value here is that. Then I want one up. And then I want one lower. And then I want two up, I think. Yep. And then I want to drop to 0. And at the end, I want a little bit again. How little? Up to that level again. Right, so so this is our function x. Right, for every little graph, every g, it assigns some non-negative value. Say integer values, if you like, it doesn't matter. Okay, then the expectation is the value of this integral. Right, that's the definition. Very simple. And there are various ways of computing that are all going to be relevant. So let me write down one and call it the definition. So that's the product over all G, no, sorry, what am I doing? The sum overall, yeah, G and P in our space of this, the measure of that in the integral, right? So that's the measure of G. So times the value. So x of G times the measure of this little graph. Okay? So we go through all the G's and we add the values of all these columns here. That's the sort of Riemann definition of the integral. Another way of computing that is to go through all the k yeah. So and just add up the measure of the event that x is at least k. So what does that do? This adds the rows. So for k equals, if this is, say, 1, 2, 3, and so on. So for k equals 1, we take the measure of all these g, whose x is at least 1, so that's all these, not those, and that one. For k equals 2, in addition, because we're summing, in addition, we'll take the measure of all these g's here, not those, then this one again, not those, and that one again. So we're adding the value of this area here, and so on for all the k's. Add columns. Add rows. And if we like, we can also sum over, combine those g's that have the same value. So rather than writing x is at least k, we can write p of x being exactly k. So for k equals 2, we want that, and we want that, and we want that, right? So then we'll have to take the value, in this case 2, times the measure where this happens. Just a moment. Right, so is that right? Yes. Okay, question. Oh, no, right, yeah, we don't want this. This is not exactly 2, yeah. Thank you. Mm-hmm. Super, thank you. Let curly H be a set of graphs on subsets of V. So very concrete graphs again. And let's count them. So x curly h, I think, or just x. No, just x. X assigns to every g the number of graphs in curly h it contains. Right? So that counts the subgraphs of G in curly H. Okay, so let me draw a picture for that as well. So it's slightly different from what we had a moment ago in the same place, and that here we really have the set H now. We don't have the value of x, right? So for a little h naught, say here, that might be in this little g, and it might be in that little g and in this one and not in the others. Right? So that's the set of g's such that h naught is contained in G. Well, it's not very blue, is it? Okay. Right, and that has a certain measure. And similarly in yellow, if we look at this particular G here, call that G naught, then it might contain these particular elements of curly H. So that's the set of H such that H is in G naught. Okay, right, and now we want to calculate the expectation. So E of x, let's do the first row first. So we'll sum over all the g's in our space the value of the random variable that we have. So what's that? That's exactly this here. So the number of h's that are contained in G. And we multiply that with the probability of this particular G occurring. So that's this. Right? And similarly, we can sum over the rows. Now, this is not the same as that second thing there, right? Because we have different rows now. The rows correspond to the elements of curly H. So we'll sum over all the elements of curly H. Well, what do we sum? The measure of those G that contain it. The probability of the event that this particular H over which we're summing at this time is a subgraph of G. Right? So if you like, we're adding the products of all these little boxes that have a cross in them. And that is the probability of one particular G times a 1 if that H is there, if there's a cross there. Right? So we're counting 1 for every H that lies in our particular G. Or here, if we go through the H's and look at the G's where this H occurs, then we count a 1 for all those G's, and then times their probabilities, but that by additivity is the probability of this set of little G's, namely those that contain our H. Okay. Right, questions about that? Okay, let's do that then for a particular curly H. Namely the set of K cycles. On subsets of V. Okay, and so that is 11.1.4. The expectation of the X for this H for K cycles is, well, I'll write it down first, then we'll sort of prove it formally in a moment. That's the probability of a fixed set of edges making a cycle. So that is P to the K times the number of ways in which such a cycle can occur, and that is, I call that NK divided by NK like this, I think. No, really? Divided by 2K, where NK is the number of ways in which we can choose the n edges or vertices, the n vertices of our K cycle. So that is n times n minus 1. So for the first vertex, we have a choice of n times n minus 1 times, and so on, times n minus k plus 1, give or take 2. Yeah. Okay. All right. So when we have chosen a first vertex, a second vertex, a third vertex, and so on, when we have chosen k vertices and make them into a k cycle in this way, then this particular k cycle arises in 2k ways. Namely, you can start with any of these k vertices and go around clockwise or anti-clockwise. Right, that's where the 2 comes from. So there are 2k ways of making a particular choice of vertices into a k cycle. For a particular way of choosing these vertices, this can occur in 2k ways like that. So that's the number of k cycles, of possible k cycles. On subsets of V. Right. Now, in order to compute the expectation formally, we'll chop it up into, we'll chop up the random variable x into little random variables that can just count one particular cycle. So for every potential cycle C, let EC count 1 if this particular C lies in our graph, and 0 otherwise. So that's how I write it. So if C is in the graph, and zero otherwise. Sorry, what am I doing here? XC. Right? Okay. Then X is the sum of all these XCs. Right? And since we're counting, there is no issue of disjointness of events or something, right? If a particular graph G contains 2 cycles, then it counts in X for the one cycle and it counts in X for the other cycle. So that's fine because we want to count both cycles in X for our graph. Okay, and then, notice that, and the reason for decomposing X into these little indicator random variables for individual C's is that the expectation of XC is really easy to compute. And that is just the probability of C being a cycle in our graph. Why is that? So this is supposed to be some funny integral, but XC only has 2 values, 0s and 1s. So what does the integral measure? It counts 1 for every little box where this is the value is 1. Up there. Right? So when a random variable has only 0s and 1s as values, then the expectation is the measure of all those G's, of the set of all G's where it's 1, trivially. Yeah, but that is nice. Because we know this. This is p to the what? K cycles. P to the k. Okay? So now, the expectation of x is the expectation of the sum of these xc's, right? That's because x is the sum of those xc's. And this is pompously called the linearity of the expectation, so we can swap the sum with the expectation. That's just a basic property of integrals. So that's the sum of the expectations of xc, and we have the expectation of xc computed as pk. And now the question is simply over how many cycles are we summing? Well, over all these cycles. Right? So that's nk, 2k. And that's it. Questions? No. Okay. So, how does computing the expectation help? Let me give you, I think I can do that here. We start with a trivial observation about the expectation, and then turn that trivial observation on its head and get out something useful. Okay, I really need that picture up there. Yeah, never mind. So when we have a certain value, then the expectation of x is the entire integral here. But if we just look at this particular value, then we just get a subset of the area over which this integral expresses. So the expectation of x is certainly at least, it contains this area and something else as well. So the expectation of x is at least a times the measure of x being at least a. All right? The probability of this is that, where it does happen that x is at least a, and then we just multiply by a, and we get this part of the integral that expresses the entire expectation. expected value of x. Okay, why is that interesting? Well, it's not really interesting, but the dividing this by a makes it interesting, and that gives us that the probability of x being at least a is small, is bounded above by the expectation, which is easy to compute, times that little a. And if that is small, then the probability of x being less than a is large. And it may happen that we're interested in when this occurs, that x is small. So we want the probability, we want the measure of the graphs, all the graphs G, where x is small, we want that to be large, and this is a way of getting it by proving that the measure of those where it's not small is not large. Okay, questions. Oh, lots of questions. There's probably something terribly wrong.
Should it be divided by a in the second step?
Lovely, thank you. Any other questions? No, okay. Right. Yeah, so, and of course those that have done probability will know this as Markov's inequality. Okay. Yeah. So, anything else?